Welcome to Phenom AI, home for AI. So I've got a fascinating puzzle for you today, one that really changed the game in computer vision. For the longest time, we had AI models that were specialists. Some were great at reading text, others were built to see images. But what if you could take a model that was born to understand language and teach it how to see? How do you get an AI to read a picture, almost like it's a sentence? Well, that's exactly what we're going to break down.
The answer to that puzzle is a model called the Vision Transformer, or VITE for short. And in this explainer, we're going to pull it apart piece by piece. We'll start with the craziest idea, how it literally turns images into sentences. Then, we'll look at how its global vision is totally different from older models. We'll uncover the secret of a special little summary token that does all the heavy lifting. After that, we'll peek under the hood at the engine itself, figure out why it only needs half of the original transformer architecture, and finally, we'll see why this one idea changed everything. So, let's jump right in.
All right, so the first and most brilliant leap the Vision Transformer makes is this. It stops looking at an image as just a grid of pixels. Instead, it decides to treat it like a sentence made up of visual words. But, how do you find words in a picture? Well, it turns out you just make them. And here's how that works, step by step. First, you take a regular image and you just chop it up. You slice it into a grid of smaller, non-overlapping patches. In this case, 196 of them. Now here's the crucial move. Each of those little 2D squares gets flattened out into one long line of numbers, a vector. And just like that, you don't have a picture anymore. You have a sequence, a sentence of 196 visual words. But hang on, there's a big problem. The model has no idea where these patches came from. A piece of the sky from the top left looks the same as a piece of the ground from the bottom right. That's why the very last step is so important. You add what's called a positional embedding. It's like giving each patch its own little GPS coordinates so the model can rebuild the map in its head. Now this is a huge deal and a big difference from the original transformers that only dealt with text. For a sentence, word order is pretty simple, right? First word, second word, third word. You can use a fixed mathematical rule for that. But for an image, the relationships are way more complex. Is a patch above another one, to the left, diagonally across? Instead of forcing some rigid system, VIT lets the model learn the positions. The embeddings are trained from scratch, so the model literally figures out the geography of an image all on its own.
So, we've turned our image into a sequence. This new format is the key to everything that follows, because it allows a VIT to see in a way that's totally different from the models that came before it, the famous convolutional neural networks, or CNNs. Let's really dig into that difference.
Think of a CNN like a detective with a magnifying glass. In its first layers, it sees tiny local details, an edge here, a bit of texture there. As the information flows deeper, it starts piecing those clues together to get the big picture. It works from the inside out. A VIT, on the other hand, sees the whole picture right away. From the very first layer, thanks to a mechanism called self-attention, every single patch gets to look at and compare itself to every other patch. A patch from a cat's ear can immediately connect to a patch from its tail. This gives it a global understanding of the image right from the get-go. Now, having that global context is incredibly powerful, but it creates a new headache. The model processes all 196 patches, and it ends up with 196 rich, context-aware vectors. But the goal is to classify the whole image. You need one decision, cat, not 196 different opinions. So how do you boil all that information down into a single confident answer?
Well, the solution is a really elegant trick they borrowed from famous language models like BERT. They introduce a special extra token whose entire purpose in life is to listen to all the other patches and create a final summary. This is called the CLS, or classification token.
The best way to think about the CLS token is like an empty bucket. It starts off as just a random vector, knowing nothing. But you place this empty bucket at the very beginning of your sequence of 196 image patches. And as they all go through the transformer's processing, this bucket gets to interact with every single patch. It learns to collect and absorb the most important bits of information from all over the image, gradually filling itself up.
Let's actually trace its journey. We tack this CLS token onto the front of our line of patch vectors. As the whole sequence gets processed layer by layer, the token acts like a sponge, soaking up context. By the time it comes out the other end, it's not random anymore. Its final state is a rich, dense summary of the entire image. And here's the key. At the very end, the model ignores all 196 of the original patch vectors and uses only this one final CLS vector to make its decision.
It feeds that single summary to a simple classifier, which then spits out the label cat. Simple and effective.
So all of this interaction, this information gathering, this summarizing, it all happens inside the main engine of the VIT. And that engine is the transformer encoder. This is the powerhouse that was basically lifted straight out of the famous "attention is all you need" paper that changed the world of language processing forever.
The heart of this engine is multi-head self-attention. That's the mechanism that lets every patch look at every other patch. The multi-head part just means it's doing this in parallel, multiple times. Think of it like having several different conversations at once. Maybe one head focuses on textures, another on shapes, another on colors. The results of that are then passed through a standard neural network, and you have some other bits and pieces like residual connections and normalization to help keep the whole training process stable.
But this incredible power has a very, very steep price. Because every patch has to compare itself to every other patch, the amount of computation required grows quadratically. It's like being in a crowded room. If you double the number of people, you don't just double the number of conversations, you basically quadruple them. This is why VITs can really struggle with super high-resolution images. It just creates a computational explosion.
Now, if you're familiar with the original transformer, you might be scratching your head and thinking, wait a minute, where's the other half? The original architecture has two parts, an encoder and a decoder. But for image classification, the VIT just uses the encoder. Why throw half of it away?
Okay, let's quickly remember their original jobs. The encoder is the reader. Its job is to take in the entire input, like a whole sentence in French, and build a deep contextual understanding of it. The decoder is the writer. It takes the encoder's understanding and then starts generating a new sequence, one token at a time, like writing out the English translation word by word.
And right there, that's the key. For image classification, we don't need to generate a new sequence, we just need a single label. We want the model to say cat, not to write a sentence like this is a picture of a fluffy cat. The encoder does all the hard work of understanding the image and creating that rich summary in the CLS token. Once you have that, you're done. The decoder's job is simply not needed.
That's not to say decoders are useless in computer vision. Far from it. They are absolutely essential for any task where the output is a sequence or has some complex structure. If you want to generate a caption for an image, you need a decoder to write the sentence. If you want to segment an image, you need a decoder to output the map of all the pixels. And of course, for huge generative models like DALL-E or Midjourney, decoders are the heart and soul of creating the final image. It really just depends on the task at hand. So by taking this powerful language model, stripping it down to just its encoder, and then cleverly teaching it to read images as if they were sentences, researchers basically unlocked a whole new way to do computer vision.
But this newfound power came with a really big catch. You see, CNNs have a kind of built-in instinct for images. They're hardwired to look for local things like edges and textures. VITs have no instincts. They start as a completely blank slate and have to learn everything from scratch. This makes them incredibly hungry for data. On smaller, medium-sized datasets, they actually tended to perform worse than the good old CNNs. But when you could feed them absolutely massive web-scale datasets, they start to learn patterns and relationships that were beyond what CNNs could see, and they eventually blew past the state-of-the-art. And this right here is the bottom line. The success of the Vision Transformer was a massive moment in AI history. It proved that you didn't need a super specialized architecture like a CNN that was custom-built only for images. It showed that a more general, scalable architecture, the transformer, could master both language and vision, as long as you gave it enough data and enough computing power. It was really the beginning of a great unification of AI architectures.
So that leaves us with a pretty profound question, doesn't it? If the same core engine can learn to master sight and language, what's next? What about sound, robot movements, video? The Vision Transformer didn't just teach an AI a new trick, it showed all of us that the fundamental architecture for intelligence might be far more universal than we ever dared to imagine.